So now you should see what you saw before, but actually probably you see it smaller because it's within this PowerPoint. However, it will allow me a bit more interactivity. So, yeah, so we were talking about this, and we could actually look at the circuit or the states in more detail. So say we have some 0, 0, and then for the qubit that we're using to facilitate the measurement, 0, and we do a couple of controlled knots on that, then, well, nothing happens. So in that case, we get the same, 0, 0, 0. Whereas if we had something like 1, so let's actually look at a superposition to make things interesting. So a superposition of the two cases in which things are different. So A, 0, 0, 1 plus B, 1, 0, 0. So here, these two are the ones that we're comparing, and this one is the additional one. And yeah, so I've put a gap here just to help us remember which is which. And then if we were to do two controlled knots on that, well, let's do the first controlled knot, which uses this as the target, and of course this is the control. So in this case, the first element in the superposition, this controlled knot would do nothing because it's targeted on a 0. So that 0 stays 0. This isn't even involved. This 0 stays 0. But if we look at the second term in the superposition, then something does happen. So this is now targeted on a 1. So the controlled knot will flip this value. So this 1 stays 1, the 0 again not involved, and this one flips. So now the additional qubit, if we were to measure it at this point, it would be different. It would collapse the superposition because by becoming 0, it would collapse down to this. By becoming 1, it would collapse down to that. But if we then do the second controlled knot, so 0, 1, we're now being controlled on this guy here. So the fact that we're controlled on this means that the controlled knot does actually do something. It flips this 0 to a 1. And in the second term in the superposition, well, again, this is the one that's being controlled. It's a 0, so nothing happens. So this 1 remains a 1. And then we find in both cases, it's a 1. So if we measure this, it will give us a 1. And it will tell us no information about what's going on over here because it's not even entangled to that anymore. It's completely independent of it. So it just gives us this information without actually changing the superposition. In fact, if we wanted to do some fancy maths, we could basically take that factor out using a tensor product and write this as the original state that we had. Well, at least if we ignore the additional qubit, tensored with this 1, which is our outcome. Okay, so this is our parity measurement. It's our syndrome measurement in this form. It's what we do in order to get some trace of errors. And errors, I have been assuming so far that errors are just bit flips, which is a very simple form of error. Actually, it's more likely that we would get not a bit flip, but something like when we're supposed to have, say, 0, 0, we have a rotation which makes this some sort of, let's say, sine theta 0, 0 plus cos theta 0, 1. And where if theta is 0, then this is close to 0, 0, but some small perturbation of being 1, 1. Now, if we were to take this and do one of these parity measurements, so introduce another qubit and ask whether it's the same or different, then if it comes out same, it collapses down to this, and if it comes out different, then it collapses down to that. So in this case, this is a superposition that's getting collapsed, but it's not a superposition we wanted. It's not a superposition we care about. So in this case, even though it's a rotation, it's a rotation around the x-axis or the y-axis. It's not it's not just a bit flip. The way that we measure the effects of noise kind of like collapses it down to being a simple bit flip. So if that went over your head, then just I'm using bit flips because they're easy, and if that made sense, then well, good. Okay, so we do these parity measurements to get a clue about the errors that have happened, and the results of these are used to identify where errors are likely to occur and how to remove their effects. But to do that, we don't want to do it manually. We don't want to be sitting there looking for all these. Well, this is the same as that, and this is the same as that, and this is the same as that. So no, we want to feed these into a computer, a normal computer, and have it figure it out for us. So this process of doing that is called a decoding algorithm. Well, it's an algorithm whenever a human does it or a computer does it, but yeah, we usually would use a normal computer to do it. And then once we have this decoding algorithm, which takes the information, works out where the errors have occurred, and then tries to correct them, we can protect against simple errors like bit flip errors for an arbitrarily long time. And there is a reason why I'm kind of assuming that it's bit flip errors, very simplified way at the moment. We'll get onto that later. So yeah, these measurements, any measurement you do in an error correcting code in order to get some information about the noise without trying to get any information about the information about what you've actually encoded. So you don't want to, when you're making a measurement which does not tell you anything about your logical qubit, it's not a logical qubit measurement at all. All it's telling you about is noise that has happened. We call this a syndrome measurement, and the result of the measurement is called the syndrome. So all error correcting codes have them, but they differ depending on which error correcting code you are looking at. So in this case, they involve 2 of the qubits of the encoding, but usually they will involve more than that. You'll be taking a group of qubits in your code and measuring some joint property of those qubits, which you know should be something, and you're checking to see if it still is what it should be. So yeah, they provide the clues that allow us to solve the mystery of where errors have happened and how to correct them. Okay, so let's think more about decoding, and to do this, we can start with an unrealistically simple case, which is so always we're getting more complicated in terms of errors. So we're assuming at the moment simple bit flips occurring at very particular points in time, and we're seeing how we can deal with those, and then we generalize to more complex errors over time. So at the moment, we have this circuit where well, I should actually explain this a little bit more. We start off with our all 0 state. Maybe I should make the cursor black again. We start off with our all 0 state. And if we want to encode a 0, then that's fine. It's already 0 repeated many times. If we want to encode a 1, it's not fine. We have to use bit flips. We have to use X gates to flip it. So here, we're imagining this is like an exponent. X to the power of b is doing nothing. X to the power of 0, sorry, is doing nothing. X to the power of 1 is doing 1x. So in the case that you want your bit value is 1, then you'll need to flip these guys to all become 1s instead of 0s. And then you repeat this process of checking to see that pairs, well, whether they're the same or different, in order to get information about whether noises have happened. And we'll assume at the moment that it is between successful implementations of these syndrome measurements that noise might have a chance of happening. If we take that very simple view, then we get quite an easy way of decoding, but it's also a simple form of the more general way of decoding. So let's focus now just on identifying errors and not trying to correct them. The way we can do this is, the best way to do this is to look for changes between different measurement rounds. So let's see how this works. Let's say we had all 0s, and then an error happened here and gave us a 1. It doesn't actually matter whether they're 0s or 1s. It just matters where the errors are happening. And then our syndrome measurements we're making tell us that these two are not the same. We measure the syndrome for these two, and it tells us same. We measure it for these two, same. We measure it for these two, it tells us that they are different. For these two, different. Same, 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 and so on. So we see some trace of errors here. The fact that these are different from each other, these are different from each other, and these are different from each other, is a signature that an error has happened here. Now so that round of measurements is complete. Then we start, because we're constantly repeating this, we're constantly repeating these measurements. So we then do the next round of measurements. Well, what do we find? Well, we would expect that these will be the same because that's how we set them up in the beginning, and they were still like that last time. So we expect them to still be like that. And we expect these to be the same because that's how we set them up at the beginning, and that's what they were last time. So we expect them to still be like that. And we expect these two to be different because even though we set them up to be the same at the beginning, we measured that they were different last time, and we haven't corrected that error yet. We've just logged that it's there, and so we still expect it to be there. So the fact that these are different in this measurement round is not a signature of error. It's a signature of things being the same as they were. It was a signature of error when we first saw it, but it's not a signature of error anymore. It's old news, it's expected, whatever. And still, these are the same, that's fine. These are the same, that's fine. These are different, well, that's new. We haven't seen that before, so that is a signature of error, as it is for when we see that these are different, these are the same, these are the same. So from this, we can see that what is the good thing to do is actually to track differences. So when we find things that we don't expect, so here, when we find these differences that we don't expect, then we say, okay, this is something, this is a significant event, let us log these 2 times that we saw something that we didn't expect. When we saw the same result again, well, who cares? So we don't log that. But over here, when we're seeing this for the first time, that's significant, so let's log that. Now, an interesting case over here is when another error happens, right next to the error that happened before. So now when we ask these two, are you the same or different? They say they're the same. And then usually you think being the same is a good thing, right? Because that's how we set them all up at the beginning. But since we have already previously seen them to be different, this is a change. Something has changed this. Something has changed these values. And we aren't going around changing these values. So it's a signature that an error has happened. Similarly, when we see that these are different, then that is also a signature. That's something new. That's a signature that an error has happened. So we log these 2 things. Even though these are the same, it's a signature of something changing. It's significant. We log it. And so we go on looking at all these syndrome changes. And what we find is that when we look at the syndrome changes, they always occur in pairs. And in these cases, only one little error is happening at a time. So these pairs are fairly close to each other. So if we look at this, it's fairly easy to see, okay, we've got a pair of syndrome changes here. There's probably an error here. We've got a pair here. There was probably an error here. A pair here, error here, pair here, error here, pair here, error here. So with this, we can figure out where the errors most likely happen. And this is a very simple example, but we don't really need an algorithm to do this. We can see it by eye, but nevertheless, well, there you go. Now, let's introduce something more realistic. So, for example, what if when we made the syndrome measurements, they didn't they didn't happen perfectly? So before we've been assuming that when we make these syndrome measurements, they happen perfectly, and then between different rounds of syndrome measurements, errors can happen. Well, let's assume now that the syndrome measurements do not happen perfectly, but some things can happen, some things can go wrong with them. So as a very simple model, we'll just assume that sometimes they lie. Sometimes when they should tell us 0, they tell us 1. And sometimes when they should tell us 1, they tell us 0. There's no actual change on the qubits. They're just lying to us. So if we take the same sort of thing as before, but we introduce some of these lie errors, well, then maybe here, we saw that these two, we asked, are these two the same or different? And it said they're different, and we believe them. But let's suppose that in this case, it's a lie. So then the next case, when we look at whether they're the same or different, we see that they are the same. And then we're like, what? I thought they were supposed to be different. So when we saw that they were different, expecting them to be the same, that was a change in the value. That was something unexpected. And so we logged that. But then when they returned back to saying that they were the same because the measurement stopped lying, that's also something significant. So now, even in this case, where it's a completely different type of error, we're seeing that an error is causing a pair of these syndrome changes. But rather than being what we might call spatially located, because different places along the line because of an error that's flipping a bit, they are what we might call temporally located. They're in different measurement rounds, but they're still pairs. And so we can still go through this and say, okay, that's probably an error here. This is probably a signature that there's been one of the measurement outcomes was lying to us, and so on and so forth. So now, still we're going around identifying pairs of these values that where they are not what they should have been, but we have to identify the pairing. But the pairing is now effectively a two-dimensional problem. It doesn't correspond to majority voting anymore. It's a more abstract problem of trying to work out where the errors have happened. And this is, even if you add in now every different kind of error that could possibly happen, it still remains like this. So we basically, by finding pairs of measurement results that aren't doing what we expect them to do, we can deduce how to correct. Now, I don't think I'm going to go into full details about this, but this should give you enough to get a sense of decoding. And of course, I made this Decoding game a few years ago as a way for you to really get hands-on experience. So that's something also that you can try out if you like. We really should make an IBM version. So, okay, I think at this point, I should maybe ask if there's any questions.
So good news, we have tons of questions. I just want to remind everyone that we're not going to be able to get to every question here during lecture. So remember to bring those questions with you to Discord, post them there, or anywhere else. We can talk to each other about them. But our highest upload question, you've kind of already touched on it, but just want to put a formal question. What effect does repetition code have on the speed of an algorithm?
That's an interesting question. Well, the repetition code has issues that makes it not so useful. So probably you wouldn't use a repetition code in an algorithm. So instead, I'm going to say just in general for quantum error correction, what effect does quantum error correction have on the speed of an algorithm? And it very much depends on what error correcting code you're using. So there is the need, and I'll touch on this more later, to be able to do, when you have a logical qubit which is spread across many physical qubits, you have to do gates on those. You have to do your gates on your physical qubits. That involves doing gates on many logical qubits. And if you can find a code in which doing those gates is what we call transversal, so you can do them in a single step. You can just do a whole bunch of things across your encoded qubits, and you can do a single logical operation. Then it wouldn't, in terms of, it doesn't really affect your algorithm runtime all that much. There would be some factor that you would have to take into account, but it wouldn't affect it all that much. But the trouble is that there are some operations that are very hard to do within an error-corrected way. And so, for example, just a single qubit rotation is something that is usually really hard to do. And you have to devote quite a lot of resources towards doing a single qubit rotation. Things like controlled knots are usually very easy, but a single qubit rotation is hard. So you would need to your circuit would be a lot bigger. It would have a lot more qubits. It would take a lot more time. than it would if you didn't use error correction. But it would work at the end, which is the important thing.
Cool. And another question, can the repetition of our answer, either yes or no, or 0 or 1, can it create a repetition bias? Is such a thing even possible on a quantum computer?
A repetition what, sorry?
A bias.
Well, yeah, so, yeah, I'm not really sure, actually, of what's being asked there. So yeah, it will cause problems if you do everything by repetition. Yeah, so I think we should speed on to the surface code and show how things are really done in quantum error correction. But trying to explain decoding in terms of that first would have been harder. So let's finish off with the repetition code, and then we will get on to proper quantum error correction with the surface code.
Great. And just one last thing, James, if you don't mind clicking the red pen instead of the black one, people in the chat were saying it would be easier to follow the red pointer instead of the black one.
Yeah. Oh, maybe even highlighter. Yeah, cool. Good idea. Okay.
Thanks.
So yeah, so this gives you a sense of quantum error correction, but really quantum error of decoding, but decoding something you got to get your hands dirty with, really. Yeah, so also one thing to note is that we usually do this by graph theoretic algorithms. So if any of you know about graph theory, then you will be especially adept at grasping some of the concepts in quantum error correction. Typically, we use something called minimum weight perfect matching, but I don't think there's any real need to go into any details on that. And so let's move on. Oh, so one thing, let's actually look at an actual example. So if we had this set of errors, what would we assume happened? Well, we can see that here's a pair of weird things. So probably that means that this was an error. Here's a pair of weird things. That probably means this was a lie. Here's a pair of weird things. That probably means this was a lie. But how can we be more formal about that? So it could have been that there was an error here and here and here, flipping these three, and that's what caused a couple of things to flag up here. And similarly, errors here, here, and here. And this is less likely because there's more errors. And so we're really comparing different possible things that could have led to this happening, and then trying to minimize and find the most likely. So this is what we do by the algorithms. And there's various algorithms, but yeah, I think I'll move on and let you look into those in a bit more detail. Okay, let's talk about logical operations. If we did not just want our qubit to sit there and be 0 or 1, but we actually wanted to do things to it, how would we do that? So this is the notion of a logical operation. So when we encode in quantum error correction, we take a single qubit of information and spread it across many qubits. And so similarly, when we want to do something to that, if we want to do an X operation on our qubit, we cannot just do it on a single qubit. We have to do it across our entire encoding in some way. And the way that we do this depends on the exact code that we're using. So for the repetition code, flipping the bit is quite easy because we're just repeating 0. We're either repeating 0, 0, 0, or we're repeating 1, 1, 1. So if we want to flip that bit, all we need to do is flip everything. We flip all of our zeros to ones or all of our ones to zeros. So at any point between a pair of these measurement rounds, we can just flip all of these qubits, and so we can do an X on all of these qubits, and that would do a logical X. It would do an X on our encoded information. And the nice thing about this is if these were a little bit imperfect, then that would just effectively be the same as if we did them perfectly and then followed that up with a little error. But as we know, errors that occur between measurement rounds are pretty easy to correct. So we would not just be doing a X operation on our encoded information, on our logical information, but also any imperfections in the way that we perform that operation are removed by the same error correction process, which is keeping the qubit clean. So this is a logical operation. It is a perfect operation on our perfect qubit, which is awesome. So doing an X gate on the repetition code is easy, but what if we were to do, say, an RX gate? So what would an RX gate mean? It would mean that we want to not just, so an X gate means that if we have a 0, we want it to become a 1. And we're doing that by turning the 0, 0, 0 of our repeated encoding into 1, 1, 1. An X gate similarly means that if we have a 1, we want it to become a 0. So it means that we're turning our 1, 1, 1 into 0, 0, 0, and we just do that using an X, 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 if we're doing 3 repetitions at least. But an RX gate, or any other single qubit rotation, in fact, so let's just say a U, any single qubit rotation would take 0 and make it to some general superposition of 0 and 1. So in an encoded form, that would mean that the logical version of this has to take 0, 0, 0 and turn it into some sort of A, 0, 0, 0 plus B, 1, 1, 1. Now, this is an entangled state. The only way you can make an entangled state is by using 2-qubit operations such as controlled knots. So already, just by looking at the state, we know that it's not going to be as easy. Here we could make an X. Our logical X was just X on the 3 qubits. So this X tensor product with X tensor product with X I've written there. We would hope that our logical U might just be similarly that we do the U 3 times. But unfortunately, that is not the case, because we can see here the fact that it is entangled, it obviously needs some controlled knots in some way. And if you look at it in more detail, what you find is basically all we can do is take our encoded information and unencode it so that our logical qubit just sits on one physical qubit. Then we do the single qubit rotation, and then we re-encode it again. But in that whole time that it is unencoded, just sitting there on a single physical qubit, it is exposed. It is no longer encoded. It's no longer having error correction done. Any noise that happens then is noise that cannot be undone. Any noise, any imperfection in this U gate that we are performing just sits there. It happens, it cannot be undone. So you cannot fault tolerantly do any arbitrary single qubit gate using the repetition code. And that is bad, because we need to do those things in order to do quantum computation. Also, so this is a major problem with the repetition code, but it's not the only one. The code only allows us to detect bit flips. It imagines the only error that happens in a quantum system is flipping bits, but that is not the case. There are other things. So a bit flip is basically like an X gate. So we're imagining that the only thing that ever happens is a gremlin sits next to our qubits and with some probability px hits them with a hammer that does an X gate. That is our error model at the moment. It is a terrible error model. That is not how physics works. At the very least, we should have that the gremlin is also able to sit there and with some probability do a Z, and with some probability do a Y. In those cases, at least we would capture something more complete. If we had such errors in the repetition code, these errors would not be picked up at all. These errors would be picked up to an extent because Y is equivalent to a combination of X and Z. So it picks up the X part, but the Z part, nothing happens. So if you have some A000 plus B111, and your repetition code looks at this and says, okay, these are the same, that's good, these are the same, that's good. Or in superposition, it's equivalently saying that these are the same as well. It says that everything is fine with this. However, if errors came along and transformed it into the state A000 minus B11, your repetition encoding would come along then and look at these things and say, yeah, all good. It would not see this. The repetition syndrome measurements are not set up so that they can see any changes in phase in the superposition. However, changes in phase in the superposition are actually quite big changes, and we don't want them to happen. So the repetition code is not the world's best quantum error correction code, and for that reason we have to so it's a good first example of quantum error correction. It's a good example of syndrome measurements and decoding and things happening, and that's why I think the repetition code is going to be very important for us over the next few years as we test out the capabilities of new devices and see if they are indeed compatible with the needs of quantum error correction. But when it comes to actual quantum computing, we will not be using the repetition code. So let's just move on to what we will most likely be using, which is the surface code. So the surface code is in some ways a generalization of the repetition code. There are things that happen in the repetition code which happen in very similar ways in the surface code, but it generalizes it to make it solve the problems of the repetition code. So the noise is no longer just going to be about bit flips. It's going to be a more general form of noise, and we are going to be able to determine all of it. Okay, so for this we need a new type of syndrome measurement, and so in the surface code in the repetition code we use these syndrome measurements where we have a couple of qubits from our code, and they're being joined by an extra qubit, and we have some C-naughts going on, and we have a measurement at the end. Looks like the Enterprise. No, never noticed that before. So this is what our syndrome measurement and these qubits in the code carry on their lives after this information extraction event has gone, which no longer looks so much like the Enterprise. We could also say that what we are doing is measuring the observable Zj plus 1 for if this is comparing two qubits called J and J plus 1. So this is an observable, so let's not get too much into the maths, but Z, as you'll see if you look into some of the sections in the first couple of chapters of the Qiskit textbook, Z can be written in this way. So it's an operator with eigenstates and eigenvalues, and the eigenstates are 0 and 1, and the eigenvalue for 0 is plus 1, because there's a factor of plus 1 here, and the eigenvalue for the 1 value is minus 1. The fact that these have different eigenvalues is why they give us different results when we measure them. Now, if we were to look at the operator Zj plus 1, then this has eigenstates 0, 0 and 1, 1, both, oops, that's a little bit big. So the 0, 0 and the 1, 1 states 0, 0, well, that's a rubber, or an eraser, as I should say in this more international audience. So we have these eigenstates 0, 0, 0 and 1, 1, and then we also have the eigenstates 0, 1 and 1, 0. And So these have eigenvalue +1, and these have eigenvalue -1, and that's why when we measure this, we get a certain outcome depending on whether it's one of these states or some superposition of them, and we get the other outcome depending on whether it's one of these states, because they belong to different eigenspaces. So this is the way that we can describe this. Now, in other error correcting codes, we usually, instead of writing down the circuit and saying my syndrome measurements look like this, and then noting that they could be described as measuring an observable that looks like this, we instead say my syndrome measurements correspond to an observable that looks like this. And of course, you have to measure them somehow. This circuit seems to work, so let's use that. So usually we state what our syndrome measurements are in terms of observables of this form. So for the surface codes, these are what the observables look like. We have a grid of qubits. So all of these things on here are qubits. This is a square lattice of qubits. We arrange our qubits on a square lattice. And what do? We associate with each of those, for each plaquette, so for each square on the lattice, we associate a type of measurement, a syndrome measurement that we're going to make. And it corresponds to this observable, which is the tensor product of Z operators. I've written them as sigma Z here rather than just a Z, because often I write sigma Z instead of Z for physical qubits and Z for logical qubits, but I'm not going to follow that convention completely throughout this. So for every plaquette, we associate a type of syndrome measurement, and that's also true for these sort of truncated plaquettes at the top and the bottom. And for every vertex, we associate a different type of measurement, and that's also true for the truncated vertices on the left and the right. And yeah, you can look at these and you can think, well, I have no idea what they are saying, but don't worry, we are going to figure them out. So what we are going to do is we're going to, so the surface code only works if you do the measurements associated with the vertices and the measurements associated with the plaquettes, because these are going to pick up on certain types of errors, and these are going to pick up on other types of errors, and it's only when you put them together that they are going to pick up on everything and be a good quantum error correcting code. However, the way we're going to try and understand what's going on here so that we can really see what kind of states are generated when we measure these things is we're going to imagine a surface code that only has this kind of measurements, and we're going to see what that can be used for. It can't be used to store a qubit, but we're going to look at it anyway. And then we're going to forget about those, and we're going to look at a surface code that only has these kinds of measurements. And we're going to think of what that can be used for. And then once we have looked at these two sort of half surface codes, then we can combine our knowledge back together to think of a surface code which has everything that it needs, and see that this can store a qubit and can store it in a way that is protected against all sorts of noise. So yeah, actually, in a lot of ways, this lecture is a bit different in spirit from the previous ones, because at the end of this, we're pretty much saying, look, we have one qubit, and we can do X gates on it and Z gates on it, which is a bit of a letdown after you've learned Shor's algorithm and stuff. But at least this time, our qubit is perfect, and we have made it perfect. But I think it's probably a good idea, since we're coming towards the top of the hour, and since I'm going to begin another section, basically, let's do questions for a few minutes, and then let's take another 15-minute break.
Sounds great. Again, tons of questions. Thank you, everyone. I want to let you know if any of these questions seem confusing, James, just let me know. I may be just mispronouncing them, so just let me know. Yeah. First question, if you see a CNOT gate itself working on the quantum bit, why can't we say the CNOT itself will give some error resulting even if they are the same? It may give an error as if they are not the same.
So yeah, it might. So here in the repetition code before, I covered this thing that maybe the measurement results lie somewhere over here, and that is a very simple model of how the whole process could go wrong, because it's assuming just it lies at the end and nothing actually affected the qubits. Actually, all kinds of things can go wrong, and these affect what you see here. So if you look at the syndrome, then you'll see the traces of all kinds of different forms of error, but they all and then you have to make sure your decoding knows that such processes can occur. But yeah, all kinds of things can go wrong, but none of them are disastrous in a well-designed quantum error correcting code. And you have to prove that your error correcting code is well designed before anyone takes it seriously.
Awesome. Next question we have, and I believe you have some papers on this. Have there been experimental demonstrations of quantum error correction? And if so, maybe after the break, could you share some of those references?
Yeah, so I should try and pull together some references, but probably the best thing to do is to show off my new paper in which I do exactly that, because it has the references therein. Yeah, so people have done various error correction based experiments. Ones that do syndrome measurements, ones that prepare the state of a bunch of qubits encoded in a quantum way, some that detect and correct errors in the repetition code. But no one's done the full everything yet. No one's ever combined all of the aspects, as far as I know, just because you need so many qubits in such particular configurations in order to do that. So the repetition code is great because you can detect and correct things. So you can show everything the repetition code is, you can demonstrate, even with current technology. And that's something that's going to be looked at in the lab for those of people who are looking in the lab. But also I'll share a link to, well, actually, I don't even need to share a link to a paper. Go to the repetition code chapter of the Qiskit textbook, because that tells you how to make a repetition code happen yourself. So in terms of experimentally demonstrating quantum error correction, you could do it today if you want to. Yeah.
Awesome. And then one final question is actually another kind of setup here. Just people asking a little bit about what Qiskit Ignis is and how it's used. And I know you do cover that in your lab, but just wondering if you wanted to give a quick overview of what Ignis is here during the lecture.
Yeah. So Ignis is about working out how good devices work. So it can be about characterizing the noise. So you have something called randomized benchmarking, which is what is used to get all of these numbers regarding the how good each qubit is and how good the gates are. So you can do your own randomized benchmarking. There's also this concept of quantum volume that we use to be a sort of, it's hard to summarize how good a device is in a single number, but it's also something quite useful to be able to do, to be able to describe things quite more simply to people. So quantum volume is our way of trying to describe things in a single number, and then it's basically a test which comes up with a score for how good a device is, and so Ignis does that as well. And it has quantum error correction in there, but quantum error correction as a test. You run it to be able to see how good your device is. So yeah, Ignis is mostly all about ways to test quantum computers, ways to validate they really are quantum computers. But it also does have measurement error mitigation in there, which is something that you might want to use in actual applications. It's something you can throw in at the end to clean up the results, basically, and it's almost magical how much you can clean out.